Hi everyone, my name is Lydia, and this is what I wish they had taught me about econometrics and introduction. We have been talking about the OLS, and in the previous videos, we even showed the algebraic proof to get to our beta hat formula. And to most of you, just as a reminder, what you've been seeing most of the time is the beta hat being how much the x and y move together over how much x move on its own, or covariance xy over variance of x, and most lastly, the summation notation that we got at the end of the proof. But to some of you, this might feel a little bit unfair and be, well, Lydia, we've also seen one more notation and you haven't really been talking about that too much. And you're right, that is the matrix notation, and you will mostly see the beta hat being defined as these x prime here, x minus 1, x prime y. So today we're going to talk about the matrix notation that is used in econometrics. This is mostly used by courses that have the green book or the Mostly Harmless Econometrics book as their book of reference. Now, keep in mind, matrices might sound scary, and these might make things look like a nightmare to all of you, but there is a reason why econometrics loves matrix notation, and that is because matrices introduced a compressed way of writing the OLS system. They make it a little bit more intuitive, also visually, but I can totally understand that this might scare a few of you, but this video is exactly to make sure to distill away some of those scary myths that the students have. So what we're going to talk in this video is mainly going to be the OLS matrix notation, a little bit of an introduction, and in another video, you're going to see the actual proof for the matrix notation as well. Let's start from the scalar model that we have seen so far. So we've been writing our model as yi being equal to beta 0 plus beta 1 xi plus the error term in here. And remember, we have the i's in here for both the y and the x variables, and also the error term in here to indicate that, well, we have information about every element for that particular variable. So how do we write that in terms of matrices now? Well, basically what we're going to do is stack that information into vectors. So it's another way of describing in a more compact way your Excel spreadsheet, basically. What happens is you've got values, y1, y2, y3, and so on until the very last person or entity in your data set. So these are all stacked into a vector. And you've got some intercept that applies basically to all of them. So you would have beta null, until the end, beta null. And then you've got these beta 1 times xi. So what is happening in there is basically you have some value beta 1 that technically is multiplying your x1, x2, until here your xn. And finally, you've got stacking of all of your error terms. Okay, so these are all vectors, column vectors, at the moment, and we can very easily assess the dimensions for each of those vectors. The first dimension comes from the number of rows and then the number of columns. So it's very easy to see for the y column vector in here, we've got n lines and just one column, so dimensions n times 1. For the beta here, we've got n times 1 as well, and then n times 1, and then n times 1. However, most of the times you will not see it expressed like this because there is an even easier way and more straightforward way. So by combining together these two elements, we can actually rewrite this stacked version into vectors as following. If we have the beta null that is actually being applied to every single element, then we can simply have a column of all ones. And we can simply multiply it with beta null in the end to get that beta null addition for every single element. Then we can stack in a second column our x variable until xn in here. Then this matrix, we can multiply it by another column vector, which is beta null beta 1. And then we'd have, as usual, our error terms stacked vector. So notice here the dimensions of the matrices we're working with do slightly change, because in this second case scenario, which is what you will see most of the times, you have that your x vector, so to speak, or matrix is an n times 2 matrix. And you've got the beta column vector, which is a 2 times 1. And as usual, this is n times 1. Notice, because here you've got the 2 and the 2, and the multiplication of these metrics with the column vector, in the end, the dimension out of this multiplication will just be n times 1, which is another way of double checking that we're writing this correctly, because we need to have an n times 1 result for us to be able to add it up to our error term vector that we have in here. So as you can see right now, just using the basic concepts of matrices and vectors, we can very easily stack up all of the observations and rewrite this in sort of like matrix shape. However, we can make it even more compound by writing the entire regression, instead of this like stuck up vector version, into the last version, which is y equal to x vector. The reason why in most of the books you'll always see the x bolded, and then the beta is mostly in italics to indicate that it's just not a number, it's actually a vector where all your betas are being stored. And again here, this is bolded, and most of the times it follows up with another definition where they say, well, the x is a matrix where your x variables are basically being stuck, plus the epsilon. Okay, so this is literally the entire regression model in one line. And from just this little introduction that I gave you, it becomes very clear why we like the matrix notation and why it matters. We can very easily address like many regressors without us having to add like beta 1, beta 2, beta 3, and so on. We just in our head add the columns, and we simply say, well, that column has been added to this X matrix in here that contains all of the other regressors, okay? Now, at the same time, using the matrix notation lets us prove OLS result without having to use linear algebra and for what could be for some of you painful summation notation, okay? At the same time, the matrix notation will clarify a lot more other concepts in terms of like multivariate OLS regressions, projection matrices, orthogonality conditions, or when we will talk in the future about the variance covariance formulas. So far, we have had a case we talked about projection matrices and orthogonality conditions. In a follow-up video that we'll do and we make the connection to them, it's going to become even more clear why the matrix notation makes sense. So ultimately, let me show you one last way of like how exactly the X matrix is collecting these regressors as a column vector. So in here, your X is basically having a first column vector, all ones, and then you've got x1, and then you've got x2, and then you can have x3, or even like other types of variables, z, w, you can call them whatever you want. But this is like how easily it is to show them without having to add beta null, beta 1, and keeping track of like the indices of the betas, okay? Keep in mind in here, each column is a variable, and each row is an observation, which for some of you will remind you of the video where we talked about the visual representation in the Excel spreadsheet of your different types of data sets. And this is exactly the rule that we defined back then on how you organize your data in an Excel spreadsheet. I hope this video has made matrix notation a little bit less scary for all of you. Remember, this is just a smarter way of keeping track of exactly the same numbers. And with this notation, the OLS formula also becomes a lot more simple. We'll see the proof in the next video. And until then, see you next time.